In this video, we are going to explain IIR filter realization structures. IIR means infinite impulse response. So here we have different types. The first one is direct form 1. Direct form 1 structure. The second one is direct form 2 structure. Third one is cascade form realization structure. Fourth one is parallel form realization structure. Fifth one is lattice ladder realization structure. So these are the different structures. So here we will see the one by one. The first one is direct form 1 structure. Direct form 1 IIR filter realization structure. So okay, here we know that for an LTI linear time invariant recursive system, that means output depends on the past outputs, present input and past inputs, that is said to be here recursive system. So LTI recursive system, that is described by the linear constant coefficient difference equation. So here that equation is for an IIR filter y of n output is nothing but that depends on past outputs, present input, past inputs. So here after simplifying, so the equation is y of n is equal to minus summation k1 to n ak y of n minus k plus summation k0 to m bk x of n minus k. So okay, here if you expand the summation and then here if you observe, so here are a1, a2 and so on, an are the past output coefficients, b1, b2 and so on, bm are the past input coefficients, b0 is the present input coefficient, right? So then here expand this series, then you can get like this. a1 minus a1 y of n minus 1 minus a2 y of n minus 2 and so on. minus an y of n minus n plus b0 x of n plus b1 x of n minus 1 plus and so on bm x of n minus m. Okay, so now here consider or assume b naught x of n plus b1 x of n minus 1 plus and so on bm x of n minus m as one new signal, that is a dummy signal w of n. Then this y of n is nothing but minus a1 y of n minus 1 minus a2 y of n minus 2 and so on minus an y of n minus n plus w of n. Okay, in this way you may write the equation, y of n equation. Now if you apply the Z transform on both sides, then you can get here y of n becomes y of z. Now here is some delay units, y of n minus 1, y of n minus 2 and so on. So okay, here apply the Z transform for this equation, right? So delay units are there. So delay units means here from the property, what is that? Y of n minus n naught as the Z transform, z power minus n naught y of z. X of n minus n naught has the Z transform, z power minus n naught x of z. Since x of n has a Z transform, x of z, and y of n has a Z transform, y of z. So from the here a shifting property in the Z transform. So here, so these are the results, right? So then here based on this property, y of z is equal to, here see what is that, minus a1 y of n minus 1. Okay, now here minus a1 z inverse y of z minus a2 z power minus 2 y of z and so on minus an z power minus n y of z plus w of z plus w of z, where w of z is nothing but b naught x of z plus b1 z inverse x of z plus and so on b capital M z power minus m x of z. Okay, so that means consider this one is A and this is B and this is C. Okay, so we are applying the Z transform here for the equation. For equation C. Okay, so that means here you can get the equations for y of z and w of z. Okay, so now for these equations we have to realize, right? So using the structure direct form 1. Realization structure means here to design the particular filter, right, based on this particular equation, we should develop one system. So here if you observe this equation, it contains Z inverse values, that means Z power minus 1, Z power minus 2, like that. Z power minus 1 means delay unit. So here if you take x of n, so here it is called as delay. Now x of n becomes x of n minus 1. So okay, here use the delay units, delay by 1 unit only. So these are available, so use only this single unit delay units. That means here if you want x of n minus 2, what we can do, use this single unit delay here 2 times, that means Z inverse, and then use again another Z inverse. That means here is a x of n, if you use single delay unit, it gives the answer like x of n minus 1. Again apply this x of n minus 1 to the another single delay unit, that is a Z power minus 1, then you can get x of n minus 2. In such a way, based on these delay units, you can get x of n minus 1, x of n minus 2, and so on, x of n minus m. That means if you want to establish x of n minus m, we need m delay units. In the particular n variable, it is x of n. If in the terms of what is that, z variable, it becomes x of z. That means here x of n or x of z is the input, and then what is the output, x of n minus 1 in the time domain. In the z domain, it is nothing but z power minus 1 x of z, right? So here if x of z is input, the output is z inverse x of z, right? Similarly, if you may use the notation like this one also in the time domain, x of n is input, output is x of n minus 1. So we may represent in these two ways, right? Okay, so now these are called as delay units. So here we use delay units to find these z inverse, z power minus 2 and so on values, and of course here is a multiplier, right? Multiplication. So here multiplication with the coefficients, that means we have to use the multipliers, right? So here multipliers. So one major unit is delay, another one is the multiplier. Multiplier means here the notation is this one. Here this is the, if it is B naught, here is a x of n, the output is B naught x of n. Okay, otherwise we may represent like here is x of z, here is B naught x of z. That means apply z transform on both sides. Okay, it's okay. Now in this way, so multiplier is used. Here this is the block diagram or signal flow graph representation of the multiplier, right? Now in addition with these two, here is another important operator. What is that? Adder. What is that? Adder. So adder symbol or block diagram is like this. Okay. So here is a x of n. Here is a x of n minus 1. Then what is the output here? X of n plus x of n minus 1, like that. Okay. So okay, here use the adder symbol like this. Here we have the two input adders only, right? So here we are multiplying so many terms, and also we are adding so many terms, right? So b1 into this one, multiplication. Okay. So and then next one is adders. So we are adding these terms here. Suppose m terms, n terms, like that. That means here see m plus 1. Here m plus 1 terms are there. So to add these all elements, we should use only two input adders only, right? So we do not use like a multiple adders. Okay. So since here we are having two input adders only, right? That's why use the two input adders. So for simplification and for designing purpose, so two input adders are recommended. That's why based on these two inputs adders only, you have to develop this multiple input adders. Okay, right. So now we will see how can you realize the structure, direct form 1 structure based on the elements like delay, multiplier, adder. See here. Here conclusion is we have the delay and we have the multiplier and we have the adder blocks. It is represented as like this. It is represented as like this. It is represented as like this. These are the block diagrams. If here is x of n, here z power minus n x of z over x of n minus 1. If here is x of n and then here the multiplying coefficient is b naught, then here is b naught x of z over b naught x of n, and here is x of n and here is y of n. Then the output is x of n plus y of n, or x of z plus y of n, x of z plus y of z. Okay, so right, so by using this right, direct form 1 structure, direct form 1 structure. Here equation is, so I am considering the y of z variables equation, y of z is equal to, what is that? Minus a1 z inverse y of z minus a2 z power minus 2 y of z, and so on, minus an z power minus n y of z plus w of z, where w of z is nothing but b naught x of z plus b1 x of b1 z power minus 1 x of z, b2 z power minus 2 x of z, and so on, bm z power minus m x of z. So here this is the IIR filter output, right, with respect to input. So in this way we can describe the IIR filter. So here from these equations, right, from these equations we should develop the, what is the direct form 1 realization structure. So see here, firstly I draw the diagram. Okay, I draw the diagram for W of z. See here, what is the input here? Here I am writing x of z or x of n. Remember, x of n means when I write x of n, that is nothing but x of z also. Okay, right, x of n. Now to get the W of z, I have to multiply this x of z to b naught. That means here use the one multiplier, so with the coefficient b naught, right? Now this is added to this term. What is this? b1 z inverse x of z. How can we get z inverse x of z? Here we just add one delay unit. Use one delay unit here to get the z inverse x of z. Here the value is b naught x of z. Now here this z inverse x of z should be multiplied with the coefficient, what is that? b1. Now these two are added. This b naught x of z that means here is b1 z inverse x of z. Z inverse x of z is applied to this one. Now here b1 z inverse x of z. This b1 is multiplied to this. Then you can get this one. Now here use the adder. Then you can get, what is that? b naught x of z plus b1 z inverse x of z. Am I correct? Now add one more term. What is that? Here b2 z power minus 2 x of z. Here is a z inverse x of z. So to get z power minus 2 x of z, again use one more delay unit here. Here the input is z inverse x of z. If you delay this one, then you can get z power minus 2 x of z. Now do the multiplication with the b2 by using the multiplier b2. Then you can get b2 z power minus 2 x of z. So here again use adder, then add these two, right? Add these two. Then here you can get this one. Okay, 1, 2, 3 terms. So these two are added, then you can get the resultant one, this summation result. Then the summation result is added to this B naught x of z, then you can get the summation of these three here. In the similar way, just use the here is the Bm minus 1, here is a last one, what is that? Bm. Now here summer, here also summer. Z inverse, Z inverse. Okay, so here z power minus m minus 1 x of z, here z power minus m x of z. So here is Bm z power minus m x of z. It's okay, right? So in this way, just use the adders, multipliers, delay units, then you can get the total sum. That means here what is the resultant one? W of n or W of z. Okay, then just again develop the next equation here to get the y of z. So in the similar way, that means here is a W of n and then here output is y of z. This y of z is delay by 1 unit. Now here is a y of z, z inverse. Now then use the multiplier minus a1. Now here you can get minus a1 z inverse y of z, that is added to the w of z. Here is a w of z. Now use the summer. Now add. So here what is the resultant one here? Here is a w of z plus, now here minus a1 z inverse y of z, right? So plus into minus, minus. So in this way you just add remaining terms also like this, then you can get the total result here like this. That means here add one more delay to get z power minus 2 y of z, and then add multiplier minus a2 and then do the sum. Okay, in the similarly here minus an minus a power a minus a n minus 1. Here y of z, z power minus n. Okay, so now then here you can get the all the terms like a2 z inverse y z power minus 2 y of z and so on. Okay, so then you can get the result y of z. So in this way we realize the IIR filter. Okay, this is called as direct form 1 structure. If you observe here, to realize this type of particular filter based on this direct form 1, it requires So here how many memory units here? Memory means delay units. How many? So here is a for this filter m delay units. Here also n delay units, n delay units. Am I correct? That means total memory units how many? M plus n in this case. And then how many multipliers? How many multipliers? Here an, here that means 1 2 3 4 up to n. Here is b1 b2 and so on, m plus n. For this b0 another one, that means m plus n plus 1 multipliers are needed. Now coming to adders. How many adders? Here for this particular w of n, to get the w of n, how many adders here? See, m adders. Am I correct? So for these two, single adder. In the similarly for these three, two adders. From b0 to bm components means here m adders. And then here how many adders? Here also. So for all these n minus 1 adders, and then again we have to add the w of z for this n adders. So totally how many adders are required? M plus n adders are required. Okay, right. Thank you. And then finally it looks like this. Okay, see this. And then we just call it as here. First part is nothing but all zero system. Second part is all pole system. So since here, if you consider this one, what is that h of z transfer function, that h of z is y of z by x of z, then y of z by x of z, if you observe that particular rational function, what is that, y of z by x of z, a1 a2 and so on, an coefficients are at denominator, and b0 b1 b2 and so on, these components are at numerator. So that's why here you know that here in the denominator, if you find the roots, then those are called as poles. In the numerator, that is zeros. That's why here this is said to be all pole system and this is said to be all zero system, right? So here if you observe the h of z equation, you can get the clear idea here. It's okay, we will see that one later. So this is nothing but, what is that? Direct form 1 realization structure. Thank you.